There are several theories about the end of the universe due to ongoing scientific research and our evolving understanding of cosmology. These theories attempt to predict the ultimate fate of the universe based on current observations and physical laws. In this video, we will cover 10 of the most popular end of the universe theories. Watch till the end and share your comments on what you think. Will the universe end like the simulation shutdown theory suggests, implying our universe may not be a physical reality, but a computer-generated simulation? Or will the universe continue to expand and explode? So, adjust your headphones, get comfortable, and enjoy the ride. The universe began with a monumental explosion, the Big Bang, and it might end in an even more catastrophic event, the Big Rip. This theory proposes that in around 22 billion years, the universe could be torn apart, atom by a force that's already driving the cosmos toward this violent fate. It's not just stars and galaxies that could be shredded. Everything down to the very fabric of time and space might unravel. The universe has been expanding since its explosive birth. And this expansion isn't slowing down, it's speeding up. This acceleration is driven by something called dark energy. Mysterious and invisible, dark energy makes up most of the universe, but it's still a baffling concept. All we really know is that it's making space stretch faster and faster, pushing galaxies apart at increasing rates. But if this dark energy grows stronger, it could eventually overpower gravity, the force that holds everything together. This unsettling possibility hinges on a delicate balance between dark energy and gravity. Gravity binds galaxies, stars, and planets together, but dark energy is pulling them apart. For now, gravity is strong enough to keep things intact. However, some scientists believe that dark energy's influence is increasing. If it continues to intensify, the cosmos could reach a breaking point, a moment where even the tiniest building blocks of matter are no longer safe. At the heart of this theory is the idea of cosmic viscosity, how resistant the universe is to expansion and contraction. Think of it like a fluid that sticks together. When scientists explored how this cosmic stickiness behaves in extreme conditions, like the explosive environments of supernovae or neutron stars, they stumbled upon a disturbing conclusion. At certain speeds, this fluid-like behavior could tear apart everything in its path. This insight strengthened the idea that dark energy could cause a big rip. To understand the Big Rip, we need to grasp the strange nature of dark energy. Imagine the space between galaxies expanding, and as it does, dark energy fills the growing void. As galaxies drift farther apart, this invisible force accelerates their separation. For now, it only affects the vast distances between galaxies, leaving smaller, more compact structures, like stars, planets, and atoms, intact. But if dark energy keeps growing stronger, even those tightly bound systems could start to unravel. In this scenario, galaxies would be the first to go. As dark energy grows, it pulls them apart, stretching the space between them until their gravitational bonds snap. Clusters of galaxies, once held together by gravity, would begin to drift into the void. Eventually, individual galaxies, including our own Milky Way, would start to disintegrate. The stars within them would slowly drift away until even the closest ones are swallowed by the expanding universe. As the Big Rip draws closer, the destruction speeds up. Planets orbiting stars would spiral away, losing their gravitational grip. Eventually, Earth itself would be pulled apart from the Sun. The atmosphere would escape into space, tectonic plates would shift violently, and the planet would crack apart. In the final moments, even the molecules and atoms that make up all matter would be ripped apart. Electrons would be torn from nuclei, and the forces that bind protons and neutrons would disintegrate. the universe would dissolve into a chaotic mess of particles, and then space itself might cease to exist. This cosmic doom isn't just a far-fetched idea. It's supported by current data, which shows that the expansion of the universe is accelerating, driven by dark energy. While some models predict that this expansion will eventually slow down or stop, others, like the Big Rip theory, suggest a far more dramatic outcome. Competing theories exist. One such theory is the Big Freeze, where the universe continues expanding, but instead of ripping apart, it cools down and fades into an eternal void. Over trillions of years, galaxies drift so far apart that no new stars form, leaving the cosmos a cold, dark, and empty place. Another is the Big Crunch, a scenario where the universe's expansion slows and reverses, pulling everything back into a fiery collapse. But for the Big Rip, the future is one of violent disintegration. The key to this cosmic puzzle lies in understanding dark energy. Scientists have been trying to measure it by studying the movement of distant galaxies and the overall expansion of the universe. But dark energy remains elusive. We can't see it or feel it directly, and yet it governs the fate of the cosmos. Physicists are hunting for clues about its nature by measuring the universe's expansion history and the behavior of galaxies over time. Some clues suggest that dark energy behaves like a cosmological constant, meaning its strength stays the same across time and space. If that's true, the universe will keep expanding, but not violently enough to tear itself apart. But what if dark energy isn't constant? What if it grows stronger? In that case, the Big Rip is not only possible, but inevitable. In recent years, scientists have considered the possibility that dark energy might be more dangerous than previously thought. Some have proposed that its equation of state, a key factor that determines how it behaves, might allow for a value that would lead to the Big Rip. If dark energy becomes what some call phantom energy, with an equation of state less than -1, it could trigger a chain reaction that tears apart the universe much sooner than anticipated. So, could the Big Rip really happen? It's hard to say for sure. Current measurements suggest that if the Big Rip is in our future, it's still billions of years away. But the uncertainty around dark energy means we can't entirely rule it out. If this destructive force grows stronger, the universe as we know it could meet a violent end. For now, the cosmos continues its silent expansion, driven by forces we barely understand. But the possibility of a Big Rip serves as a reminder of how fragile everything is, from the galaxies in the sky to the atoms that make up our bodies. The universe may seem vast and eternal, but it's not invincible. And in the end, it might tear itself to pieces. One of the most chilling possibilities is the idea of vacuum decay, or as some call it, the Big Slurp. Imagine the universe as stable, solid, and unchanging, but beneath the surface, it might be ticking toward a sudden and catastrophic collapse. This theory arises from the study of quantum fields, specifically the Higgs field, and suggests that the universe might not be resting in its most stable state. What if everything we know, all of space and time, could one day be wiped out in a flash? To understand vacuum decay, you need to first grasp the Higgs field. This field stretches across the universe, shaping reality by giving particles their mass. It's a bit like an invisible fabric woven into the cosmos. But here's the catch. The Higgs field might not be in its true lowest energy state. Instead, it could be sitting in a false vacuum, something like a ball resting on a hilltop, balanced but not fully secure. It's stable for now, but not forever. At some point, the universe could tumble from this false vacuum into a true vacuum, a lower energy state. This fall would be instant, unstoppable, and completely destructive. The shift from a false vacuum to a true vacuum is what scientists call vacuum decay. Once started, it would send a bubble of this new, deadly vacuum racing across the universe at the speed of light. This bubble of true vacuum would rewrite reality as it spreads. Inside, the laws of physics as we know them would change. Constants that govern how atoms stick together, how stars burn, how planets form, all could be altered or erased. The result? Everything in the path of this bubble would dissolve into chaos, possibly disintegrating or transforming beyond recognition. Stars, galaxies, and even atoms might simply vanish. And since this bubble moves at the speed of light, there would be no warning. By the time it reaches us, it would already be over. This catastrophic event, dubbed the Big Slurp, captures the sudden and consuming nature of vacuum decay. It's not just a wild sci-fi idea, it's based on real science grounded in quantum mechanics, a field that explains the behavior of particles on the smallest scales. Quantum fields, like the Higgs field, can shift between energy levels in ways that defy classical physics. Over long stretches of time, a transition from a false vacuum to a true vacuum could occur. Not because of anything we do, but as a result of random fluctuations in the universe itself. There's another clue that suggests our universe might not be as stable as we'd like to believe: the mass of the Higgs boson. When scientists discovered the Higgs boson in 2012, they found that its mass, about 125 GeV-C2, is strangely close to the threshold that indicates instability. This mass puts the universe in a precarious position, suggesting that we could, in theory, be living in a metastable, temporary state. The early universe, too, offers hints of this instability. During cosmic inflation, the universe expanded at an unimaginable rate, driven by a vacuum-like energy state. If this inflation ended in a false vacuum, it means the universe has been in a metastable state ever since. We might be living on borrowed time, waiting for the inevitable fall into a true vacuum. But even if vacuum decay is real, it won't happen everywhere at once. The universe is expanding, and some galaxies are already moving away from us faster than the speed of light. If a vacuum bubble forms, it would only affect regions it can physically reach. Distant parts of the universe, separated by vast distances, might remain untouched for eons. For some, the end could come much later than others. Despite how terrifying it sounds, vacuum decay isn't just a fringe theory. It's built on solid quantum mechanics and fits within the standard model of particle physics. This model, which explains how particles interact through forces, doesn't rule out the possibility that the universe could be metastable. It's not speculative science fiction, but a serious, mathematically grounded idea. What makes this concept even more captivating is the sheer unpredictability of it. We could go about our lives entirely unaware, and then in an instant, everything could be gone. The thought that the universe could end with no warning is both terrifying and strangely fascinating. It captures the imagination in a way that few other ideas do, leaving us to ponder the fragility of existence. Scientists continue to explore this possibility, studying the Higgs boson and quantum fields to better understand our universe's fate. New breakthroughs could reveal whether we are in true danger or whether we are safely nestled in a stable vacuum. Either way, vacuum decay keeps physicists on their toes. It's a reminder of how much we still have to learn and how little we control. The Big Slurp is a haunting possibility, grounded in real science. Though it might be far off, the mere fact that it could happen leaves us with a sense of awe and humility. Imagine a universe dominated by black holes, swallowing stars, planets, and everything else. Over time, they consume vast regions of space, devouring matter relentlessly. But here's the twist. Black holes themselves are not eternal. They slowly evaporate. This process is driven by something called Hawking radiation. It's a quantum effect that causes black holes to emit tiny amounts of energy, gradually losing mass. Eventually, they vanish entirely. As the universe ages, this evaporation accelerates, draining even the mightiest black holes of their strength. In the far, far future, all black holes will have evaporated, leaving behind a cold, dark, and empty cosmos. This is the ultimate fate of everything: stars, galaxies, and even the smallest particles. What remains is a bleak, lifeless expanse where not a single atom remains intact. Hawking first discovered that black holes aren't completely black. They release energy because of quantum fluctuations at the event horizon, the boundary that separates what's inside a black hole from the rest of the universe. These fluctuations involve the creation of particle-antiparticle pairs that pop in and out of existence everywhere in space. Near a black hole, however, things change. One particle of the pair falls into the black hole, while the other escapes. This escaping particle represents the energy lost by the black hole, slowly causing it to shrink. This slow, steady loss continues for eons, but it's unstoppable. In this future where black holes dominate, they may even outlast everything else. Stars will die, galaxies will drift apart, and eventually black holes will be the only remaining entities in the universe. But black holes aren't immune to the relentless ticking of time. Due to Hawking radiation, even the largest black holes will evaporate, though this process takes trillions of years. What's fascinating is that recent studies suggest this radiation effect might apply to all objects with mass, not just black holes. This means everything in the universe, from the tiniest particle to the most massive star, could slowly dissipate over unimaginable timescales. Picture the far future. A universe once teeming with energy, life, and matter is now a graveyard. Black holes, the last remnants of cosmic activity, shrink and disappear. No light, no warmth, no motion, just an endless stretch of nothingness. This is what scientists call the heat death of the universe. Once all matter evaporates, the universe enters its final phase, cold, dark, and empty, where time itself seems meaningless. The interplay between quantum mechanics and gravity has brought the cosmos full circle, from the explosive birth of the Big Bang to a quiet, cold death. This theory paints a haunting picture of the universe's end, driven by the unstoppable forces of Hawking radiation. The ekpyrotic scenario, rooted in string theory, suggests that our universe wasn't born from a single Big Bang, but from a violent collision between vast, higher-dimensional objects called brains. These brains exist in a multi-dimensional space, beyond the familiar 3 dimensions we experience. In this model, the universe didn't emerge from nothing. Instead, it came from the energy released by 2 brains crashing into each other. This impact caused a massive explosion of energy, which we perceive as the Big Bang. This collision will rip apart everything we know. Galaxies, stars, planets, all of it will be obliterated by the immense energy released. The collision is not a gentle event, it's a violent, universe-ending smash. All of space and time will collapse, compressing everything into a singular, chaotic moment of destruction. But in this destruction lies the seed of new creation. The energy unleashed from the brain collision will spark the birth of a new universe. Just like how ours was born billions of years ago from a previous collision. The universe won't end in a slow freeze or a gradual fade. Instead, it ends explosively, through a catastrophic brain impact that destroys everything and gives birth to a brand new cycle. This cyclic nature of the ekpyrotic model means the universe is fated to collapse and reset, over and over again, in an eternal loop. Each cycle of cosmic destruction leads to the birth of a new universe where everything starts fresh. Our universe is just one in an endless sequence of cosmic rebirths, but its end is guaranteed by the inevitability of the next brain collision. The ekpyrotic scenario predicts that this cosmic collision will not just end life as we know it, but wipe out every particle, every force, and every trace of our current universe. The end is sudden, total, and violent, yet it is also the beginning of a new universe. The cycle repeats, forever. Phantom energy is a terrifying possibility for the universe's fate. It's a hypothetical form of dark energy, but far more extreme. Unlike regular dark energy, which causes the universe to expand at an accelerating rate, phantom energy would accelerate this expansion at an ever-increasing, uncontrollable speed. As the universe expands, galaxies move farther apart. But with phantom energy, the rate of expansion grows so fast that it will tear galaxies away from each other. It doesn't stop there. The force would keep increasing, pulling apart stars, planets, and even molecules. The universe itself becomes unstable under the relentless expansion. Scientists believe in this possibility because phantom energy fits within some interpretations of general relativity. It suggests a universe where the equation of state parameter, which governs how energy density relates to pressure, drops below -1. When this happens, the repulsive force of expansion becomes so strong that not even gravity can hold things together. At first, only galaxies get torn apart, but the expansion continues to accelerate exponentially. Eventually, even solar systems can't survive. Planets are ripped away from their stars. As time goes on, this expansion reaches smaller and smaller scales. Eventually, it will reach down to the atomic level. Atoms themselves are torn apart. The very structure of matter is shredded, as even protons and neutrons are torn to pieces. The universe disintegrates completely. What's even scarier is that this future is inescapable once phantom energy takes hold. No force, no matter how strong, can resist it. Gravity fails, and even quantum forces cannot prevent the universe's annihilation. Scientists study this possibility because it presents a stark alternative to the slow endings usually predicted. Phantom energy introduces the idea that the universe's expansion, instead of slowing down or leveling off, might accelerate out of control, leading to an abrupt and catastrophic end. Some models of dark energy and general relativity predict the conditions under which phantom energy could exist, giving this scenario a basis in current theoretical physics. In the end, the universe could be ripped apart, atom by atom, by the overwhelming force of phantom energy. The result? A complete and total disintegration of everything, leaving behind nothing but a void expanding into infinity. It's the ultimate cosmic destruction, driven by a force that no one can stop. The Poincar recurrence theory suggests that if the universe has finite energy and exists within a fixed volume of space and time stretches infinitely, then everything that has ever happened could happen again. The idea comes from a principle in mathematics and physics proposed by the French mathematician Henri Poincaré in the late 19th century. It challenges the traditional ideas of how the universe will end, offering a cyclic view of time rather than a linear one. Imagine the universe as a system with a finite amount of energy. This includes all the galaxies, stars, planets, and particles. According to the laws of thermodynamics, energy cannot be created or destroyed. Over time, the universe changes and evolves, but the total energy remains constant. Now, if time is infinite, and the universe can only configure itself in a finite number of ways due to its limited energy, then, theoretically, the universe must eventually return to a previous state. In other words, if time has no end, the universe would cycle through every possible arrangement of matter and energy repeatedly. This process is what scientists call the Poincar recurrence. At first glance, this might seem counterintuitive. How could something as vast as the universe simply reset itself over and over again like a cosmic loop? The reasoning behind it lies in probability and the nature of dynamic systems. In a system with finite energy, the number of possible states it can occupy is limited no matter how large it is. Over an infinite amount of time, the system will eventually revisit one of these earlier states because it has nowhere else to go. It's like rolling a set of dice. Given enough rolls, the dice will eventually land on the same number combination again, no matter how improbable that outcome may seem in the short term. This cyclic nature of the universe presents a radically different view of how it might end, or rather, not end. If the Poincar recurrence theory is correct, the universe will never have a permanent death. Instead, after vast periods of time, the universe would reset to an earlier state, including potentially the same state it was in during the Big Bang. The universe could expand, collapse, or change in countless ways, but ultimately, it would repeat itself. This means that not only would large-scale cosmic events repeat, but even the most minute details of existence, down to the atomic level, could happen again. Every event, every moment of time, would eventually recur, playing out identically to how it has before. The implications are profound. It suggests that the universe is, in a sense, eternal. Not in the sense of remaining unchanged forever, but in constantly looping through the same cycle of changes. The Big Bang that birthed our universe could be just one iteration in an infinite sequence of similar events. After unimaginable periods of time, the universe could once again experience a similar explosion, giving rise to a new cycle, indistinguishable from the one we live in now. This theory is fascinating because it directly opposes other ideas about the ultimate fate of the universe. The most commonly discussed models, such as the heat death or the Big Crunch, propose a final state of stillness or collapse. The Poincar recurrence theory, however, suggests that even if the universe were to reach a state of maximum entropy, where all energy is evenly distributed and no further work can be done, it would not stay in that state forever. Given enough time, random fluctuations could cause the universe to return to a lower entropy state, beginning the cycle anew. The relevance of this theory stems from its foundation in mathematical physics and thermodynamics. It's built on a logical framework, with the concept of finite energy and infinite time driving the idea. Scientists are intrigued by this model because it offers a solution to the question of what happens at the end of the universe without invoking any new or speculative physics. Instead, it relies on the established principles of probability and energy conservation, making it a plausible scenario within our current understanding of the universe. However, it's important to note that the Poincar recurrence time, the amount of time it would take for the universe to return to a previous state, is unimaginably long. We're talking about timescales so vast that they make the current age of the universe, around 13.8 billion years, seem like an instant. The recurrence time is calculated to be far longer than the lifespan of stars, galaxies, or even black holes. In fact, it could be so long that it surpasses any practical sense of what time means to us. Even if the universe were to eventually repeat itself, it would be after a time span so incomprehensibly vast that everything we know today would be long forgotten, reduced to dust. This brings up an interesting philosophical question. If the universe repeats itself after such an immense amount of time, does that recurrence really matter? From a human perspective, the idea that everything we experience will eventually happen again is both mind-bending and almost meaningless in practical terms because no one could ever witness it. Despite the almost incomprehensible timescales involved, scientists consider the Poincar recurrence theory because it fits within the framework of deterministic physics. If the universe is governed by the same laws of physics at all times and places, then given infinite time, it makes logical sense that every possible state of the universe will eventually be revisited. In this way, the theory provides an intriguing solution to the question of cosmic finality. Instead of fading into oblivion or collapsing in on itself, the universe could be destined to loop through its history forever. The cosmic fragmentation theory suggests that as the universe continues to expand, space itself might break into isolated regions, each following its own fate. Driven by dark energy, this accelerated expansion could cause parts of the universe to fragment into separate, disconnected areas. These regions would be so distant from each other that no communication or interaction could occur between them. Essentially, the universe would divide into cosmic islands, each cut off from the rest. This theory is based on the current understanding of the universe's accelerating expansion. Observations of distant galaxies reveal that they are moving away from us at increasing speeds. If this trend continues, the universe could reach a point where even light can't travel between galaxies. This expansion would leave galaxies and star systems completely isolated. Over time, the universe could fragment into distinct pockets of space that evolve independently of one another. Some regions could experience a runaway expansion, stretching space so drastically that all matter within them is torn apart. In other regions, however, local gravity might still dominate, leading to gravitational collapse. This divergence is the core idea behind cosmic fragmentation. Parts of the universe expanding endlessly, while others collapse into dense singularities. The theory suggests that different parts of the universe would experience different ends, rather than a single, uniform fate. Cosmic fragmentation is scientifically plausible because it aligns with general relativity and our knowledge of dark energy. General relativity predicts that the universe's expansion will continue to accelerate, and dark energy is seen as the driving force behind this. Additionally, quantum mechanics suggests that space isn't perfectly smooth. Tiny fluctuations could cause the universe to fragment over time. These quantum irregularities, combined with the effects of dark energy, could lead to the formation of independent cosmic regions with varying destinies. One of the most compelling aspects of cosmic fragmentation is the unpredictability it introduces to the universe's end. Traditional models, such as the Big Freeze or Big Crunch, predict a uniform end for the entire universe. But cosmic fragmentation suggests that the universe's fate could vary across different regions. Some areas may expand infinitely, becoming cold, empty voids. Others might collapse into singularities where gravity overwhelms all other forces. This unpredictability challenges the notion of a singular, deterministic end and instead presents a chaotic and diverse cosmic future. The model also has connections to the multiverse concept. If space fragments into isolated regions, each pocket of the universe could evolve with its own set of physical laws or constants. This would mean that different regions of the universe might not only end differently, but also behave differently as they evolve. This idea resonates with some interpretations of string theory, which suggest that different regions of space could exist in different vacuum states, leading to diverse physical realities. Cosmic fragmentation is relevant because it offers an explanation for the universe's potential end that accounts for both the accelerating expansion and the unpredictable nature of quantum fluctuations. Instead of a singular end for the entire cosmos, this model suggests a fragmented universe, where each region experiences its own independent fate. Some regions might become eternal expanses of empty space, while others could collapse into regions dominated by black holes or dense matter. The scientific backing for this theory comes from the principles of dark energy and general relativity, as well as the role of quantum mechanics in shaping the structure of space. As dark energy continues to push galaxies and clusters apart, it becomes increasingly possible that space could stretch to the point where different regions lose all interaction with each other. Over time, the universe becomes a fragmented, disjointed collection of isolated pockets, each experiencing different fates depending on local conditions. The holographic end theory suggests that the universe might not be what it seems. According to some interpretations of string theory, everything we perceive as three-dimensional could actually be a projection from a two-dimensional surface, much like a hologram. This idea, known as the holographic principle, fundamentally changes how we think about space, time, and reality. If this principle holds true, the end of the universe could come from the degradation or alteration of the information stored on this surface, effectively erasing our reality. In this model, the entire universe, its particles, forces, and structures, is encoded on a vast cosmic surface. The three-dimensional world we experience could simply be a projection of this information. The holographic principle originated from studies in black hole physics, where scientists discovered that information about objects falling into a black hole could be encoded on its event horizon, a two-dimensional boundary. This led to the idea that the entire universe might operate in a similar way, with everything we know encoded on a cosmic boundary. If the universe follows this principle, its fate depends not on what happens in our three-dimensional space, but on the state of the two-dimensional surface. The holographic end would occur if the information on this surface degrades or becomes corrupted, causing the universe to vanish. Like a hologram disappearing as its source degrades, the three-dimensional universe would dissolve, erased by the breakdown of the underlying information. This theory is relevant because it bridges the gap between quantum mechanics and general relativity, two fields of physics that often seem incompatible. The holographic principle offers a way to reconcile these two by proposing that all information about the universe is stored on a lower dimensional surface. This idea arose from the study of black holes, where information about falling objects isn't lost but encoded on the event horizon. Applying this concept to the universe as a whole means that if the information on the cosmic boundary changes or decays, everything within the universe would cease to exist. One important implication of the holographic model is that the end of the universe would not be a gradual or explosive event. Unlike models such as the Big Rip or the heat death, the holographic end would be sudden and complete. If the two-dimensional surface that encodes the universe fails, the entire three-dimensional reality would disappear without any physical collapse or explosion. The theory also ties into the concept of entropy and thermodynamics. As the universe evolves, the amount of entropy, or disorder, increases. If the information stored on the cosmic surface reaches a critical point of disorder, it might no longer support the three-dimensional projection, leading to the collapse of reality. This perspective on the universe's end relies on the relationship between the information on the two-dimensional surface and the projection of space and time itself. Scientific backing for this theory comes from string theory and quantum gravity, which have struggled to provide a unified framework for understanding the universe. The holographic principle offers a potential solution by suggesting that space and time are emergent properties rather than fundamental ones. If this is the case, the universe's end could come not from a physical collapse, but from a failure in the information that generates the space and time we experience. The simulation shutdown theory suggests that our universe may not be a physical reality, but a computer-generated simulation. If this theory holds true, the ultimate fate of the universe could be tied not to natural processes, but to the decision of an external entity, the creators or operators of the simulation. In this scenario, the universe would end not with a cosmic collapse or decay, but with a simple command shutdown. This idea stems from the growing interest in the simulation hypothesis, which argues that it is possible, even likely, that our universe is an advanced simulation created by a more technologically sophisticated civilization. The hypothesis gained attention after philosopher Nick Bostrom proposed that if such civilizations have the ability to create highly realistic simulations, and if they do so on a massive scale, then statistically, it is far more probable that we are living in one of these simulated worlds rather than the base reality. If we are indeed part of a simulation, then the universe's end would depend on the decisions made by those controlling the simulation. The end of the universe, according to this theory, would not be a grand cosmic event, but something as mundane as a software shutdown. In this model, the entire universe, its stars, planets, galaxies, and all forms of life, are part of a sophisticated virtual environment. The laws of physics, the passage of time, and even the fabric of space could be artificial constructs, programmed to behave in ways that appear real to us. If those running the simulation decide to terminate it, the universe could vanish instantaneously. From our perspective, reality would simply cease to exist. There would be no warning, no gradual decline, just an immediate and total erasure. Scientists entertain the possibility of a simulation because of several key observations about the universe. First, there are unexplained phenomena in physics that may point to underlying code. For instance, quantum mechanics, with its probabilistic nature and discrete energy levels, could resemble how computer simulations handle information. The limits of computational power could explain why physical constants and the speed of light are capped. They might be hard-coded parameters within the simulation. Additionally, the simulation hypothesis offers an explanation for the fine-tuning problem. Why the physical constants of the universe are so precisely calibrated to allow for the existence of life. If the universe is a simulation, its parameters may have been deliberately chosen by the simulators to create the conditions necessary for complex life to evolve. This bypasses the need to explain fine-tuning through natural processes or multiple universes. The relevance of this model is its potential to explain the ultimate fate of the universe in a way that no other theory does. While many cosmological models, like the Big Freeze or the Big Crunch, involve natural cosmic processes leading to the universe's demise, the simulation shutdown theory suggests that the universe's fate could be determined by an external, possibly artificial factor. If the universe is a simulation, it doesn't have to end through entropy or expansion. It could be turned off like a computer program when it no longer serves its purpose, or if the creators decide to run a different experiment. Scientific backing for this theory comes primarily from philosophical arguments, technological advancements, and the nature of computer simulations themselves. As computer technology advances, humans are already creating increasingly realistic virtual environments. With the rise of virtual reality, artificial intelligence, and quantum computing, it becomes easier to imagine a future where simulations of entire worlds, complete with intelligent beings, are not only possible, but commonplace. If humans can already simulate small, rudimentary universes within computers, it's conceivable that far more advanced civilizations could create simulations indistinguishable from Poincar reality. One of the key philosophical arguments supporting this theory is the computational nature of the universe. Some physicists, like John Wheeler, have speculated that the universe might fundamentally be information-based, with the phrase "it from bit" describing the idea that physical reality emerges from underlying binary information. In this context, the simulation shutdown theory makes sense. If the universe is governed by informational processes, then its end could occur when the processing stops, when the simulation is shut down. Another factor supporting this theory is the increasing prevalence of simulations in our own world. Video games, AI-driven simulations, and virtual worlds are becoming more advanced and immersive. If technological trends continue, it is reasonable to predict that future civilizations could create simulations with sentient beings, and those beings might never realize they are living in a virtual world. If we assume that this is the case, the possibility of a simulation shutdown becomes a logical outcome. However, the simulation shutdown theory introduces a deeply unsettling question. Why would those running the simulation end it? There are several possibilities. The simulation might be a research experiment, and once the necessary data is collected, there would be no need to continue. Or the simulation might simply crash like any other complex system, leading to the sudden end of the universe. Alternatively, the operators might choose to run a new simulation, one that differs from ours in significant ways, and decide to terminate this one. In all cases, the universe's fate is out of our control, decided by forces beyond our understanding. This theory also prompts ethical and existential questions. If our universe is a simulation, does anything we do really matter? Would the end of the simulation nullify everything that has ever happened, rendering it meaningless? On the other hand, could we somehow signal to the simulators, proving our awareness of the simulation and possibly influencing their decision to keep it running? A bonus. The quantum immortality theory is based on a radical interpretation of quantum mechanics, particularly the many worlds interpretation. In this view, every time a quantum event has multiple possible outcomes, the universe splits into different branches, with each outcome occurring in its own separate universe. Quantum immortality suggests that consciousness could survive in alternate branches of the multiverse, even after catastrophic events that would seemingly end an individual's life in one branch of reality. The theory stems from the Schrödinger's cat thought experiment, which illustrates the concept of quantum superposition. In this experiment, a cat is placed in a box with a mechanism that has a 50% chance of killing the cat. Until the box is opened, the cat is considered both alive and dead, existing in a superposition of states. In the many worlds interpretation, the moment the box is opened, the universe splits. In one branch, the observer sees a live cat, and in another, they see a dead one. Quantum immortality suggests that for the observer inside the system, in this case, the cat, consciousness would always experience the branch where it survives. This theory leads to the astonishing implication that an individual's consciousness never experiences its own death. While in some branches of the multiverse, the individual might die from a catastrophic event, like an accident, illness, or even the ultimate destruction of their universe, there will always be at least one branch where they survive. As long as the multiverse continues to split with every quantum event, consciousness would persist in the branches where the individual continues to live. In this sense, quantum immortality means that from the subjective point of view of the individual, they never experience their own death. One of the most intriguing aspects of quantum immortality is that it offers an explanation for what might happen to consciousness if the universe itself were to end. In catastrophic scenarios, like the Big Rip, Big Crunch, or heat death, some branches of the multiverse would still exist, where these events either do not occur or are somehow avoided. The conscious mind, according to this theory, would always continue to exist in these alternate realities. Even as some branches of the multiverse end due to cosmic events, others would continue, providing new paths for consciousness to persist indefinitely. Proponents of quantum immortality are drawn to this idea because it offers a way to circumvent the finality of death. It aligns with the many worlds interpretation, which is a well-regarded and mathematically consistent interpretation of quantum mechanics. The theory challenges the traditional view of death, proposing that while physical death may occur in one universe, consciousness could skip to another where survival is possible. While speculative, it raises profound questions about the nature of consciousness, reality, and the boundaries between life and death. An interesting fact related to quantum immortality is that it doesn't just apply to human consciousness. In theory, any sentient being, regardless of their species or origin, could experience quantum immortality. The survival of consciousness isn't tied to any specific biological or physical traits, but rather to the quantum mechanics that govern the multiverse. This leads to the mind-boggling possibility that consciousness could persist through an infinite number of alternate universes, experiencing countless realities and effectively never ceasing to exist. While the concept of quantum immortality is controversial and lacks direct empirical evidence, it raises important philosophical and scientific questions about the nature of consciousness and the structure of the universe. It pushes the boundaries of what we consider possible and challenges our understanding of life, death, and existence itself. Though it's difficult to test or prove this theory, the many worlds interpretation of quantum mechanics is a widely supported view, lending some credibility to the idea of consciousness surviving in alternate realities. So, here you have it. 10 unique theories about how it all will end. What are your thoughts? Don't forget to share, and remember to like, share, and subscribe.